yesterday we stopped here in at least one class. I was like yelling the end of it when the bell rang. Was that in here? Okay, so and I think I said I might need to explain it again. Do I kind of need to explain the end again? Because yes, okay. Were we all okay with the magnitude? We get this, right? I think it was the angle that some people may have had some questions on. Okay, so the angle here, let me get a different color. What the calculator gave us was this negative 50 degrees, right? Which is right here. And it's asking us for a true bearing, which means 0 starts up here, right? But the calculator always gives you theta. So we know that for theta, it's in the 4th quadrant. We have to also pay attention to the resultant, calm yourself down, the resultant vector here, which is a 2nd quadrant vector, right? So I need, even though this is in the 4th quadrant, I would need it in the 2nd quadrant. One option I have is to add 180 to that and go ahead and get my theta correct, which would be like 129 degrees, something like that. So that green angle right there, that's my theta, right? But I need it as a true bearing, which means I need it as what this orange one is, starting here at 0, going around, ending up in the same spot. I'm talking about the angle differently. So we have a couple of different options to get there. My intention was for you to try and figure it out, and then we would talk about it. I don't know if we had time in here for that or not, but there's different ways to get to to this actual number, that 320. So one thing you can do once you have this 129, if you subtract 90 from it, right, then you have this piece left. And if you look at the orange one, to get to 360, it would come all the way around here. So that little piece you're left with is what you would then subtract from 360 to get to that 320. That's one way to reason your way around the quadrants. But I mean, there's other ways to do it. I think one of the things, the reason it's shaded in like this is because if this is your 50 whatever, then this right here is also 50 whatever because those are vertical angles. So you could just take 270 and add that positive 50 degrees to it to get to that as well. Just another way to get to where you need to be. But the best thing for you to do is just to be able to reason through how to find those angles, adding and subtracting, knowing that each quadrant's 90, and you should be good. Okay? What questions do you have about that? Does that help clear that up? Go ahead. Oh, because 129, if we were talking theta, since it gave me the negative 50 and I want to be in the 2nd quadrant, I added 180. Does that make sense? Okay, good. Good question. What else we got? Anything else? All right, good deal. All right, let's look at number 11 then. It says a baseball player runs forward 15 feet per second and throws a baseball at a velocity of 80 feet per second at an angle of 20 degrees with the horizontal. Okay, so I'm going to draw my little perpendiculars here. Remember, not the x and y axis, just using it for perpendiculars so I can get my angles correct. If the baseball player runs forward, then he's running like this, and that is 15 feet per second. He throws the baseball at a velocity of 80 feet per second at an angle of 20 degrees with the horizontal. So this is 80 feet per second. It should be considerably longer than my 15 there. And this is 20 degrees. Okay. So I have the baseball, I have the player, and I have the actual ball. So theta for the player, what would the theta be for the player's vector? 0, right? That's a 0. And then theta for the ball would be 20, because there's no bearing involved here. That's just straight up, that is theta, because we're starting at 0 right here. Okay, everybody good with that? So then I have the player's vector, which is 15 times the cosine of 0, and then 15 times the sine of 0. The ball will be 80 times the cosine of 20 and 80 times the sine of 20. Not just yet, because let's talk about this first vector first. What is the cosine of 0? 1, right? So 1 times 15 is 15. The sine of 0 is 0. So 0 times 15 is 0. So that's really that vector. And we didn't even have to write the trig stuff out because this vector right here, your vectors in component form have an x component and a y component. Well, your x component is a positive 15. Your y component is 0 because you don't go up or down any. Does that make sense? So you could have jumped right to that one. So just think about that. When you have horizontal and vertical, they work easy like that. One of the two is 0. The diagonal ones are the ones that we really have to use the trig for. So now we are going to add them. And double check that your calculator is in degrees, just in case, you know, somebody came to work on something else and used your calculator, put it in radians. Yes, so you could just do 15 plus 80 cosine 20. Make sure you store it. Shift store X, shift store Y. You should get 90.175. And make sure you are getting these numbers. And if you were having issues with this, let me know. I don't want you missing stuff because of punching numbers in the calculator. Once you get that and we agree, then go ahead and find your magnitude and your angle. All right, so the magnitude you get is the magnitude, right? You got to make sure you put the right labels on it. Then the calculator always gives you theta, and it will always give you something in the first or second quadrant. You have to double check what quadrant you're actually interested in. This is directed towards the first quadrant. This is a first quadrant angle. I want the first quadrant. I'm good there. Then you got to double check what it's actually asking you for. It says the resultant speed, which we got, and the direction of the throw. There is nothing that is remotely talking about bearing, and so if it's not talking about bearing in any way, shape, or form, then it's just talking about theta, and that is your theta, and you're done. Okay. So it's possible what the calculator gives you is exactly what you want, but you want to double check because you have to make that decision each time. Okay. What questions do you have? All right, let's look at 12. So we have a boat heading across a river. So I'm going to make a river here. My boat heads directly across the river. They'll be directly across there. Velocity of 28 miles per hour. The river is flowing at a rate of 12 miles per hour. I want to find the magnitude and direction with respect to the shore. Okay, so I have the boat and I have the river. Right, so the theta for the boat's vector, what's that going to be? 90. This is 90. And theta for the river is 0. And because it is 0 and 90, and these are, you know, vertical or horizontal, I don't really have to write out all the trig stuff. I can go directly to the vector itself. So for the boat, the vector is just 0, 28. And for the river, the vector is 12, 0. Okay, make sense? Yes? Yes? What? Okay, go ahead. Right, because if this is I have an x component, which is 12, my y component is 0. My x component is 0 because I don't go left or right anywhere. It's not angled anywhere. I just go straight up, so all I have is a y component there. It's like hugging the x-axis and the y-axis. You got it now? Okay. So then I need to find b plus r, and that's going to be easy. It's 1228, right? Don't have to store anything anywhere. And then I'm going to have the magnitude of b plus r is equal to the square root of 12 squared plus 28 squared. And you can go ahead and give me a decimal for that because it would make the most sense in this situation. You get 30.463. Yes, good. So miles per hour. Then I need theta. So theta is equal to the tangent inverse of 20, oh goodness, can't even write the right things, 28 over 12, saying it right and writing something else. And I would not bother with reducing those if you're about to use the calculator. You don't want to run the risk of accidentally doing something ridiculous. And that will give me, yes, 66.801 degrees. All right, so then I look back at my resultant vector. It's a first quadrant vector, so that's in the first quadrant. That's good. And it says I want the direction with respect to the shore. So basically that's like the horizontal. So this is theta, and we're done. Okay. What questions do you have? Now, if you actually wrote out the trig stuff for B and R, you'd get the same answer. You just don't need to do that if it makes sense to you. Okay. Yes, ma'am. It should be fine, because if you drew the river, this way, and you went directly across the river, and the river was flowing, you should still get the same answer. Okay, it would come out the same. It's a good question. What else you got? Anything else? Okay, good deal. All right, so then let's flip it over. We've got a drone flying at a speed of 40 miles per hour in the direction of blah, blah, blah. So what I want you to do on this one is I want you to read through it. I want you to draw a diagram, but I want you to draw it where you make your little dotted lines, like we would start with little dotted lines. You're going to draw your first vector, and then wherever it ends, draw your dotted lines again, draw your second vector. So you're literally adding them as a picture so we can draw our resultant in. Do the best you can. I'll give you a minute to do that, and then maybe just a minute. You shouldn't need too long. And then I'll draw it, and if you need to redraw it below it or whatever, it's fine, but make an attempt. Yes, there's still an arrow there. Okay, but I've given you enough time to reason through it. So I have a drone that's flying at a direction of south 70 degrees west. So this would be about my angle, and it's going at 40 miles per hour. So this would be 70 right here. This would be 40. Right? So then, starting here, I have wind that is 15 miles per hour in the direction of south 10 degrees east. So it'd be like this, and 15, remember the 15 and the 40 are their actual lengths of the vectors, so this one should be shorter, even if it's not super, super accurate. You want your angles to be at least a good attempt at getting them accurate, and this be 15. This angle right here would be 10 degrees. So then when I draw in the resultant, this is the resultant vector that I'm actually finding the magnitude and direction of. So even though my picture is not fabulous and my angles are definitely not 100% to scale and neither are the lengths, but I still think it's probably good enough to think that it's correct that this would be directed towards the third quadrant at least, right? And so you can understand what's actually happening. Because remember, this is the plane trying to fly this way, but the wind's pushing it over here, and that's physically what's happening. All right, so then we have to think about, I have theta for the plane. No, it's a drone, not a plane. No. Sorry, theta for the drone. What would theta be for the drone? Yes. $200. Because you do have this 180, and then this is 70, so this would be 20. So that 180 plus 20 is going to give you 200. Okay? And then theta for the wind, what would that be? 280. Good, because it's 270 plus 10, and there is your 280. Okay. What questions do you have about that? Awesome. So now that we have the angles and we have our magnitudes, go ahead and set this one up, work it out. I'll write it up here too, but you try and work it out without just copying mine down. Okay, so the magnitude you get is the magnitude, right? Make sure you think through your angle when you get it. The theta that you get is not going to be your final answer. Okay, so the calculator gave me a first quadrant angle, right? Like 39 degrees, something like this. What quadrant is my vector directed towards? The third quadrant. So to get my theta correct, I could add 180. I mean, because this is your 30, and you could do that. When you do that, then it comes over here, right? But remember, you've got these vertical angles here. What this is asking me for, it says find the resultant magnitude and direction as a quadrantal, or as a quadrant bearing, which means that this is going to be, if I actually want to end up down here, it is going to be south something west, right? South something west. So we got to figure out that something. So there's different ways to do that. One of the ways you could do it is if this is your 39, this has to be 39. So you could just take 90 minus the 39 and get that angle right there. Again, other ways to reason around it. I just think that that's probably the one you're least likely to do. So I just wanted to point out that it's a possibility if it makes sense to you. But when you do that in the end, what should you get? Good. 50.877 degrees. Okay. What questions do you have? And again, there's definitely other ways to get to that number, but you know, we could all think about it a little bit differently, and it's fine as long as you can reason your way to it. Okay. All right, let's talk about horizontal and vertical components. So this component form is your pointy bracket form. It's called component form because it has horizontal and vertical components, right? So a vector can be resolved into horizontal component and vertical component. The horizontal and vertical components are also called rectangular components because we're using them in the rectangular coordinate system. So whatever this vector is, right, it has an x coordinate or an x component and a y component. This is your left, right. This is your up, down. Just like when you plot points, it's just not a point that you're plotting, right? So it says because the rectangular components form a right triangle, you can use trigonometric ratios to find their magnitudes. So let's look at 15. It says Danica is pulling a sled with a force of 400 newtons using a string. If the string makes a 35-degree angle with the ground, okay, so here's my ground. Here's the string making a 35-degree angle, right? And it has a force of 400 newtons. It says find the magnitude of the horizontal and vertical components. Well, there's your right triangle. This is your horizontal. This is your vertical. Flashback to right triangle trig and geometry, and bam, there you go. That's how you work this. Okay. So I want to find x. If I want to find x, I'm going to use 35 and 400. What trig ratio am I using? Cosine. So the cosine of 35 is equal to x over 400. But we actually find the absolute value of x because it could be that it's actually a negative value when you're graphing, but your speed and your force, yes, it's possible to talk about force negatively, but when you're finding these components, we're just talking about them in a positive aspect. So if I solve for x, I'm going to multiply both sides by 400, so I get the absolute value of x equals 400 times the cosine of 35. Well, guess what? That's the x component that we've been doing anyway. That's the magnitude times the cosine of theta. Right? That's your x component, or your mg cosine theta, r cosine theta. It's all the same thing. So the absolute value of x gives you 327.661. So then the actual answer here is that your horizontal component is equal to 327.661 newtons. Then we got to find the vertical one. That's y. So that would be the sine of 35 is equal to the absolute value of y over 400. So the absolute value of y is equal to 400 times the sine of 35. And you can go from there. All right. What questions do you have? I'm thinking we don't need to do 16. You agree? You got that figured out by now? Okay. It's the same thing now. All right. So if you don't already have this gluter taped in, make sure that that happens. You've got some time left. Make good use of that time and work.